Okay. So how I uh, normally the home assignments are allocated 2 weeks, so you have one more week for them, and also the chapters, the 4, 5, and 6, are also for 2 weeks. So yeah, you have 2 more weeks for them. But we decided to have this call also because I think it will be helpful to answer your questions so far, also from these chapters, and also to review the questions also if you have for the assignment, and also to review the code. So I we were all three of us, we were very busy with our day jobs, so we didn't manage to complete the review. Actually, I think we only managed to do like 1 or 2 reviews. So sorry for that. But what I propose is to first address your questions about the theory side from the chapters, and then we could do like a live review. For example, live code review. You could share your screen, and we could actually look at the code. We explain the code. We participatingly, it doesn't have to be only me. All of us, we could do like a review. So just imagine, for you who are used to working in a team, normally in every project this should happen. You should have like for each of your commit, you should have like create like a pull request like this, and then a colleague of you, at least one, comes and do a code review. So they normally, at a minimum decent level, they analyze the code, the logic, and so on. But ideally, a code review consists of fetching the branch corresponding to that PR, fetching it locally, analyzing the code, and also running the code, running the test, so making sure that everything is fine. So it takes a bit more time, but the idea is that it helps catching the aspects that you as a coder missed, which is normal because you are human. You don't operate like uh, the same efficiency every time, which is also good because sometimes you are way more efficient and you have way better ideas than other times. So this is how actually innovations come. But with any good, it is also a bad in the universe. So this is the equilibrium. So that's why for these bad situations, you have a process in place that help us reduce those, because we cannot eliminate those, because even the reviewer is a human. So even he can uh, miss something, and that's why in a bigger project where they want even more security, they use multiple reviewers, so two, three, how many they permit time. Also, they also use, for example, also in GitHub, you can have like a rule. You can have, for example, you can have multiple checks for a code review. You can have like running tests, running some checks, and so on. And also, you can have a review done by the code copilot, for example. So the copilot from GitHub could do a code review on your code, and it's actually considered as a check. So if that fails, you could also as a human pay more attention, let's say, to the review, or use what the copilot suggestions are. So it helps also. So this is a normal process. So that's why normally this code review is done async, which means that you, exactly like now, you create the code, you create the pull request, and us or the reviewers look when they have time. But there are situations where you can do the code review, let's say, one to one. So we could either meet at the same place with the reviewer and the coder, or in the same time, like we are now, not in the same place. The first is also space time. Now it's also time, and we could do a code review like this. And also there are tools, and also the modern editors like VS Code and Z and Rust and so on. For us, offers you the capability to do like code with me, somehow it's called. So you can actually share the editor, and in the same, let's say, editor and tab, you could see the position and the cursor, for example, this the selection for both of you. And you can actually collaboratively edit the code like you do with the Google Docs or something like that, which is also very, very useful. So for now, I say that we can just do like each of you, okay, who wants to share your screen, and we all do a code review on those on the code. And firstly, I would suggest to start with the questions you might have for the course part, and then we can continue with the code review. So maybe I'll share my screen with the Rust book, and maybe we can let's say go over that, and you, if you have specific questions, uh, I don't know how is practical. So we go over the course, and you ask when you have. Maybe this is more. So we could go over the course, and I can say a little bit about it, and then you can ask specific questions for the exact part that I'm showing. Does the sound okay, or you prefer another format? Please let me know.
Yeah, it's fine, I guess.
Okay. So do you see the Rust book,
Yeah.
the site?
Yes, yes.
Okay. So I'll try to explain each of the chapters, and then yeah, maybe we could look a little bit over the examples. But so I'm sorry I didn't read all these chapters now before the course, which I should have done, but it was a very hectic period at my day job. We had like a very important demo. So, but I read this at some point, like you. So normally I should be familiar. Just okay, I don't remember exactly on what index offset in the page is what, but I'll try to explain you, and then I think it's better to take a question. So uh, the there is also something. Let me show you. I wanted to show you also. Where is it? Resources, I think. Just a bit. I'll find it. Yeah, I think this is. So I found, I don't know, somewhere this chart. It's somehow related to also to Danny Kruger. Maybe I could go a little bit Danny Kruger effect. So the idea is that this is a good one. So this is what's happening to all of us actually who learn something new in any field. Is on the x you have the, so on the horizontal axis you have the knowledge, the what, how much do you know, let's say from Rust, taking this example, so the competence level, and the confidence level is on the y-axis. So the idea is that so just understand this happens to anybody, to all of us. It's just how our brains works, and the difference is that if you understand this, you can manage your expectations, and you can determine on what position on this chart you are, and you know what's the outcome of, for example, if you continue to learn more. So we start, let's say, knowing nothing. Okay, you start knowing nothing, you start to learn Rust, and quickly you will understand some concept, and you will see that okay, it's nice, quite a nice language. I heard that's very good, very fast language. Okay, I know it very well. Then you end up being having a lot of confidence, but actually you have just a few knowledge of the language, and there is also where the ignorance level, let's say, so the ignorant people remain there, let's say, in the peak of Mount Stupid. So they somehow feel that they understand a lot of this language, which is actually false because there is a lot more to know. So actually, you don't know what you don't know, which is the harder part in anything. And the idea is that after you start to understand that, okay, it was just an illusion, that it was so easy and it's only that, then you, as you learn more, because you need to also learn more, not just spend time, then you realize that it's a lot more to learn, and then you become disappointed, and you realize that, okay, maybe I will never be able to learn so much. So then your confidence goes way low, almost as at the same step as it go high, but as you see, it gone high even faster, quicker. And the idea is that your confidence gets to a level where you feel that you, at least personally, I can tell you from my personal experience, even though I have experience with multiple programming languages, over 20 years of experience, in over 20 years' time, I found Rust hard to learn. And I had like situations, especially in the Barrow Checker and Lifetimes area, where I struggled a little bit with what I know it's best to do from Java, and in Rust, the Rust compiler didn't consider the same, had different opinions, which were better in the end. And the idea is that you become to feel that, at least from my personal experience, I felt that I'm not as good as a developer maybe for Rust, so maybe I should start something else. And there are like, let's say that the times when the people quit learning Rust, so they found this concept hard to grasp, and they don't see the advantage of them. They don't have the motivation. They don't have the reasoning to actually continue to learning this hard stuff, and most of them quit. But the idea, so this is also where like the you could have like what's called imposter syndrome, where you actually feel less than what the level you are at. And the idea is that most of the times, also with the imposter syndrome, is that you are wrong. So you actually are more, you are better than you are actually are feeling yourself. And then you need to also realize that all this could be only in your head. So you should find the aspects in your past that confirm you that you still have good knowledge. You are still smarter than you're feeling now. You are still better than you're feeling now. And somehow it's also useful to feel that in the end it will be better than now. And there will be like, I know, some dots. In the end, the dots will connect. But if you look from the future to the past, you can easily see the path where you did right, and all everything you see that are converging to something, which is easy. But from the past, from that moment, present moment, you cannot actually see this converging to something. So the idea is that it helps you if you find confidence and hope, and understand that put your mental have a mental state that you feel that they will all converge and it will all be better, and use whatever you think is good for you. If you're spiritual, use it. If you're religious people, use it. Use whatever helps you. But just gain somehow trust and confidence that if you continue to learn, if you look on the axis, if you continue to increase your competence, so you learn more, also the confidence will grow. So then it will be better and better. Okay, not at the same, let's say, speed of increasing as at the start, but it will be better and better. And you should allocate time to learn and not expect results immediately. So just give time for the results to come, because they will come. And I'm a case that I can confirm you that it happened for me. I felt that maybe I should quit. I somehow found motivation by myself, uh, and moved on, and now it's better. So now I'm working actually full time in Rust position, so I'm very happy. So it's very okay. And the idea is that uh, you need to you need to uh, understand that you actually need to allocate this time and resources to learn, because if not, then yeah, it's very easy to, let's say stop it. And for me, looking now in the past, I feel that it would have been easier if I would have somebody to tell me this. I feel that it would have helped me, and at least tell me about this, and if possible also help me technically. So actually, at some point, I decided that I want to be the mentor that I didn't have, and this is how this Rust course actually came to life. This is how the idea of this course. This is why this course exists, for me to try to do my part of helping others that maybe don't have the situation, let's say the context that I had, or it's a bit helpful or useful for you to move on and get to a better places in all this Rust ecosystem. Because believe me, the light will come, and it's very beautiful. What's after that, and Rust is the learning Rust is very rewarding. So you will really get in love with Rust, and you really like it. And so, okay, I'm not like a fanatic of Rust. I see that there are places where Rust is good. I see that there are places where you better use Python. For example, at a coding interview at a company, I don't recommend you to use Rust if you also know Python. I mean, if they give you like classical algorithmical problems, just for example, if you need to implement a doubly linked list, you will see later on it's not easy at all to implement correctly a doubly linked list in Rust. Actually, just to understand that there is some hints that this language is hard. It's the first language, at least that I've seen, that there exists a book like the Rust book, which is called Too Many Linked Lists. It's in the resources that I sent you. It's actually showing you how to correctly build a doubly linked list. So a simply linked list is easier, but a doubly linked list is a bit more complicated, and you will understand actually from these three chapters why. And uh, it's a sign that for sure something is complicated here, but it has its advantages in context and in realms where is very good. But if you, let's say, get to an interview where they want to see how you write and implement from scratch, not use a library with a double linked list, it will take you a lot, and let's say do something with that double linked list. So you have that's why they're called algorithmic and data structures. So you have the data structure, then you apply an algorithm on it. So if they, I don't know, give you something that implement a double linked list and find out if you have a cycle or something like that. So first they want to see how you implement the structure. So actually maybe you have 20 minutes for this task. You will actually use all the time, most likely, or close to the 20 minutes to actually to implement just the list, and then you don't have time for the algorithm. So actually it's not a good choice. But with Python you'll do it way faster, even with C. But the idea is that in production applications you will not have only 20 minutes to do a double linked list. They will give you time, and you write tasks and so on, so you have time to it. But in the end it is performant, and it is like the performance compared to, for example, to Python of C and Rust is like 100 times. So it's a lot. So it's very useful to use Rust when in situation where it makes sense, but not in all. Or if you want to prototype something, it's very good for proof of concept application. Python is very good. I mean, Python is very good. Then you move it to I don't know, more safe language like Rust, ideally, or I don't know, if situation is you can use Go, you can use C if really needed. But nowadays, also like Twitter, I think Twitter CEO said that now the new projects that normally would have been written in C, ideally should be started with Rust or other memory safe languages. So as you see, uh, if you feel so understand this, and if you feel somewhere on this slope, just try to identify where you are, and just see that if you learn more, everything will be just better. And uh, somehow I did an analogy when I saw this graph, this chart. I don't know exactly where I found it, but it's something like, if you look, so you are at the first slope. So this is like the similar to the chart before. If you look at the graph and the function chart. So just it's a bit more expanded in a few cases. And here is like, for example, when you hit and learn about ownership, okay, it will be a bit difficult, but not so hard. So you have a bit of break, then you again have an increase in confidence, and then you. So yeah, I remember where I said this. So this was related to, if you see on the y-axis, is like this is the lifetime for you who get to that, but if not a problem, you'll get it. So this chart was related to how lifetime learning lifetime evolves in time, and in the axis time. And then actually you get to the bottom checker, which is a bit more complicated, so it gets you down even more. And then you get to the lifetimes, which are quite complicated. And then this gets you to this value of despair from the previous chart, from the equilibrium effect. But after you get past that too, then slowly, of course, there are other, I don't know, you can, I don't know, smart pointers, async programming, you'll see. You can associate for you which one it is. But then if you see the trend is up, so you'll only go up. And then you get to the point when there is stability, and then you slowly go up. This is normal. You cannot learn a lot here because there is not much to learn, actually. So it's expected. So now, given the, let me go back to the Rust book. Here it is. So now let me tell you a bit about the ownership. So the Rust, let's say, promises are like, they are telling you that they are offering you uh, automatic memory management, uh, safe automatic memory, so automatic memory management in a safe way, without a garbage collector, and with the performance of C and C++. So if for any of you who had experience with C and C++ and are reasonable thinking, and you use common sense, and you have a decent expectation of a language, you understand that this is a very bold claim. So this is very courageous for someone to say like this. And I put on the channel, I don't know if you've seen, that there was a hacker who, when he got into Rust, he read this sentence, and the sentence in what article he read was also that it saves you from all the typical problems in C, like dangling pointer use after free, that gets you in the segmentation fault issues, and accessing out of bounds. Bounds checking, so accessing elements in array that are out of the bounds of the array. So he said something like, you cannot do this. You cannot just say that you resolve all the people's problems, all the world problems, the developer problems now, and just offering solution like this. It's like, this is absurd. You just don't do that. And then he tried to, he was intrigued that if this is possible, and he actually learn Rust, I think in 2013 or something like that, before it was launched in 2015, and he actually understood that they are actually correct, and the in the end he actually loved Rust, and he used it day by day, and being like an ethical hacker. He develops the security solutions, very good security solution, and many libraries, also in fuzziness and so on. So he had a very good and proactive contribution. And if you read that sentence, you should think the same. And if you were to accept that is true, because somehow that's why you are at this course, that you want to learn it, so you have heard maybe that Rust is good and so on, so you accept that affirmation is true, then you need to understand the most logical thought that you should have is, okay, I can understand that, but or the question is, what's the catch? So how does it do it? What's the catch? So the catches are actually these three concepts, which first is the ownership, and what this gives you. So this comes from the C, actually, which is called resource acquisition is initialization. So in short, it's something like the one who allocates the memory is also responsible of deallocating it. and only it will deallocate it. So this will save you from the problem from C that could happen, that double the allocation, like calling the destructor twice, for example, and the the fact that you will make sure that only you will be responsible of what's happening with that memory. And normally, if you are being the owner, so this is the owner, the one who allocates the memory. Normally, you have right permission to this area, so only you can edit it, and this helps you with this situation. And what is actually meaning is that, I don't know, if you are in the scope of a function, you allocate a variable, something on the stack, let's say, it doesn't matter. The idea is that this function, the scope of this function, is the owner. So when this function ends, normally the owner, let's say, dies, goes out, and it automatically, I mean, Rust will do this for you, Rust compiler will do this for you. It will deallocate the memory. So it will call the, normally, if you want to control this deallocation process, you implement the drop trait, and you have a drop method which will be called by the, okay, when the program runs, because not correctly said, it will call by the compiler, because the compiler just transform the code. But okay, the compiler will make a code that will generate a call to this function, and you can control what's happening there. But so this is what's handling the allocation and the allocation of the memory. And for example, here I think they mentioned that when you allocate a string, for example, it allocates an array inside the string where it's actually keeping all these uh, characters of the string. And you can see that you can also mutate it or allocate a new memory. So behind the scenes, string is like, you will get to that. There is a structure called vec, which is actually, so normally you will use like an array. I think they mentioned here because they speak about the slice type, and the array is like a contiguous memory region where you can place your elements in the array. Let's say you have numbers or such. And the idea is that if you want, I know if you have size 10, if you want to put the 11th element, you don't have space, so you need to allocate a new array, and or put it somewhere else. So the vec, what it does is actually allocating a new bigger region, normally double than the initial one. So it starts with the initial capacity, it allocates a bigger region, and then copies the elements from the first region, drops that region, and then adds your element, the additional element, and the new ones that might come. So this is done automatically for you, and this is done automatically also in the push stir. Okay. Yeah, so this I think it was discussed a bit last time. So this is like the scope of. So for example, this allocates a string in this scope, and if you use this variable as in this scope, you can do whatever you want with it. It exists, but after you exit this scope, normally, I mean, this is destroyed, and is no longer available for you to use. So you could consider that the owner of this variable is this scope, and when this scope goes out of scope goes extinct, so this dies, it will also destroy the memory that was allocated by it. And if you do, for example, if you do this, is like this given that, so it allocates like a simple value, a numeric value, and these simple numeric values are also implementing what is a copy interface, copy trait. And the idea is that when they allocate here a new, so y takes the value of x, actually it's copying the value, so also x, it's available, and it's copying the value to y. So actually there are two memory allocation with the same value. And here in this case, this the string is not a copy. So the string in this case, it will actually be moved. I mean, the owner For the first line, the owner of the string is S1, so the S1 variable, and then the owner becomes S2. So the ownership was passed to S2. So now if you want to try to use S1 after this line, it's not valid. Okay. Uh, yeah, Bozo, you can ask. Sure.
So
Yeah, just
we have
yeah.
two different type of values. So we have the primitive types like integers, booleans, characters that are usually allocated on the stack, and when you assign them, they are actually copied.
Yeah.
Okay.
So yeah.
And we have also this the other type like string, which has a piece of a region of memory allocated on the heap. So I wonder if it's possible to have these types like a string that implements the copy trait, so that when you do the assignment, they are actually copied, although they have memory as allocated on the heap.
Yeah, I understand. So you can do this. I'll explain you how. But I'm thinking if there is a type in standard library that does this.
Like a wrapper over a value.
So the idea is that if you would to implement string, let's say by yourself, let's say you want to make your string, and you actually what you do in order to have your structure, even if it's allocated on the stack on the heap, sorry, like string, in order to have it act like the primitive in the first case, you need to implement two traits. So the first is a clone. So the clone is how you copy the value, let's say. So you can control if it's a bitwise copy or if it's a you maybe want to keep only some fields. You have some fields that are transient. Transient means that are only, let's say, present while that object exists. But if you create a copy of that object, those fields should be not moved on to the other side. So you could actually just copy few of the fields or something like that. And so you implement this. So this is you describe how the clone happens, and then you implement copy two, which actually copy extends clone. So in order for you to be able to implement copy, you have to first show to the compiler how you want to clone it, and this is actually just a marker trait, which actually what it does is when the compiler sees something like this, so for example, you see this and this string is my string, let's say, in that case, if it sees that it's copy, if you see that it has implementing the copy trait, automatically it will copy the value. So it will call the clone method
So when I
for,
do an assignment, you mean? So when
yeah,
I
so
do
it,
assignment from one variable to another, instead of moving the the values somehow, I mean moving just the pointer, it will actually call the copy method, and I can choose to
yeah,
create a
yeah,
new region of the memory with the same
correct.
contents.
Yeah, so the idea is that this normally this instruction is like you said, it doesn't move. So what move is actually is moving the owner of the this string from S1 to S2. So this is what moving is. The ownership is moved, and in the case of this string is also implementing copy. That copy is just a marker trait. It doesn't have any methods, but that extending the clone trait, what the compiler does, it will call the clone method for your structure, which will create a new structure in another place in the memory, and that structure will be given the owner to be the S2. So the ownership of the structure becomes S2. So you will end up, like in this case, with two regions of memory allocated, and each of those having a different owner, S1 and S2. And you can do this for any of your structures. So even if it's allocated on the stack or on the heap, so you can do this. And actually, this is how the string memory representation is. So on the stack, it's actually keeping the a pointer to the first element in that array with the actual values, the characters. It keeps the length of that array and the initial capacity, because initially it will allocate an array of this capacity, and you can put some, let's say, smaller values, and it will shorter strings, let's say, so it will not occupy all the places in that array, and some places will be used when you call push stir from here. So if you push stir with, I don't know, you have capacity 5, you have length 3, you push stir with 1, it will just use the next element, and also it will still have one free. But if you, in this case, if you push stir on this string, it will need to allocate a new array, which will actually be allocated in a different region in memory, and this pointer will have the value of the new first element of the value. They will have the value of the address of the new first element in the array.
So there is another question in the chat.
Yeah, sorry.
Like if if I understand correctly, the string doesn't implement the copy thread.
Yeah, and I was thinking a bit why.
And the question
and
is
then-
why.
Yeah,
The question from the chat.
understand. I don't
Can
know.
I have a guess?
Yeah,
Like a
sure.
guess. I was thinking we always target the performance, so it makes sense that we would like to move stuff as much as possible. So when I say let S2 be assigned to S1, I just want to move it. I don't want to create another region in memory. So when I say move stuff as much as possible, I say move stuff as much as the program doesn't get broken, the logic doesn't get broken. So when we have collections, not primitive types, we want to move them because of efficiency, like performance wise.
So the default, you mean that the default behavior should be the
Moving.
move.
Yeah,
I think
because of performance.
And if I want another copy, I have to call clone
explicitly. Yes, you explicitly call clone or whatever the method was.
But there are cases, if I implement the copy trait, the compiler will call the copy
we'll do that for
automatically.
We'll do that for you automatically, and that's also a catch. So a thing that you should always be very careful when implementing copy is that, for example, if you have a method with an argument of such type that is also copy, it will automatically call copy on it. So it will be transferred by value, let's say, and you need to understand that this performs automatically. You don't see any in the code. You don't see obviously that this is happening. So you don't see the dot clone or something like that. So it could be problematic for people who are new to the code and they don't know that structure also is copy, is implementing copy behind the scenes. So you should be very careful when you implement copy. You should be very cautious and sure that you really need that, because it will create the clone automatically. So if you're not very it's not very clear for you if you should do that, and if you're not very certain, you should just implement clone if you want to give the ability to actually clone it, and let the users actually call clone, because then in the code it's explicit. And actually this is what Rust tries to do also with this typing system. It tries to be very explicit also in the code, with the penalty that sometimes it's a bit verbose compared, for example, with Go.
So basically, we should avoid as much as possible to implement copy.
Yeah, and actually in many documentation they actually recommend that. Yeah, so you should only implement copy when you are very sure that that's what you want. I mean, if it's acceptable that it will happen behind the scenes. And like Anthony said, that's, I think, a very good reason actually. And if that will be, let's say, an educated guess, it would be a very good educated guess. So I don't know exactly the reason why they didn't do it, but what your assumption is, it makes perfect sense, because indeed in Rust, when you have like a normal function. So for you who are coming especially from Python, if you have a function like this, I don't know, error, and normally this automatically does a move. So by default, if you put this in other languages, for example, it doesn't move anything. Okay, they don't have this concept of movement, but it's actually giving you a pointer to that value. So it's not copying the value, but the A represents a pointer to this structure. And you use it, and then out of scope, another can use it too. And for example, if you have like this, and if you have let's say somehow is an error, doesn't matter how, and then you call test on A, and then you want to print, let's say A, let's consider it's a display too, and this is invalid actually. So if you do this, it will maybe add errors too. Okay, error needs to be created correctly, but the idea is that at this point the owner of the value of the memory where error is, it's passed to the test. So this is what is called the move. So the ownership is moved to test, and when test finishes the execution, it actually calls the destructor and actually will clear this from the memory, because the owner uh, owner is inside this function, and when this goes out of scope, the owner dies and the memory needs to be reclaimed. And actually here you cannot use A because it's invalid. And actually, if you understand this, that after this function is executed and is finished, then the memory is actually deallocated. And here actually, if you would to print what's there or to use what's there, you could actually use, let's say, what was deleted, or in a different scenario, what could happen is if you have like a multi-threaded environment, after this line is executed, then the thread is moved to executing another thing and then come back to you, and that another thing, if it allocates some memory, and if the compiler or if the memory what is given to that is the memory that it was corresponding to this error of ours, to this A, and he writes something there, you will actually read the value that they wrote there, not the value that was previously there. So you either read like a phantom, or I don't know, a reincarnated phantom, or call it how you want, but that will be a different value which most likely will be invalid. So that's the use after free, for example, from C, that this ownership mechanism protects you against. So you cannot do that actually. You can write a code to get into a situation where you will use. Okay, you don't know yet know what unsafe Rust is, but in the Rust that you know, which is safe Rust, you cannot do that because the compiler protects you from doing that. So this is one advantage of this ownership concept, which somehow it's specific to this language, and this is exactly like you said. So by default, this is what's happening is a move. So by default, actually the Rust is thought to move. So yeah, in that sense, then it makes perfect sense that also for string, it's considered that by default you should move it or also for memory advantages. And then if you explicitly want to do this, normally you would call, let's say, error implements clone. So you will call clone like this. So you pass a new region of memory. But if a error implements copy, if you do this, it will automatically do the copy for you and the clone, but you don't see from this code. So if you don't go inside error struct to see that what it's implementing, and if it's copied too, it's not obvious for you, and it just happens automatically. And maybe then you don't understand. You debug the code and you don't understand why it's a new value there, what is happening. So yeah, I think it's a good reasoning. Okay, what else they do here? Okay, so this is how the move happens. So the actual the actual array in the heap, it stays the same, and the pointer from the structure is updated, put it in the S2. So the S2 will then point to that array, but the region corresponding to the, so this, like what's in the left, is like metadata for the actual value, because from the code, when you just allocate the string, what's important for you is just that this value hello, which is this, and this is like metadata. And let's say you don't care about that, but the metadata is preserved here. So I mean, it creates a new metadata here, but the actual value is retained, and the pointer actually just is being changed from the S1 to S2, and S1 actually becomes invalid. And you can even see, let's say, if you are like a compiler, you could even mark this pointer as, I don't know, zero, for example. You can mark it to zero because it's actually a U64 value, or U size more correctly, so depending on your CPU registry size. And then it will see that it has an invalid pointer value. So okay, I don't have what to point to, so of course I'm invalid. I crash the compilation, and this only has the new value. And this is, for example, here is what is happening if you do a copy. This should be, let me read the string not to, yeah, this is a copy. So if you have copy, then yeah, it allocates a new memory, heap memory, it copies the values like you define in the clone implementation of the clone trait, and then all these are having different pointers to the different memory addresses. So that's what's happening. And yeah, this is the example that I gave you before, in the same idea that this was the owner was S1. Now the owner of this string is S2, given this. And now if you try to use S1, then it's not valid, because the ownership was moved to S2, so the S1 is no longer responsible. So you cannot have two owners. So the region of memory, and you will see after that there are smart pointers and so on, which from the outside gives you the impression that there are multiple owners accessing the variable, but or even writing to it. But actually, behind the scenes, there are just some references and just some view, like a view in the from database realm, like a view in the actual data. So to the actual owner, so everything goes through the owner actually. So it's just like you are intermediary between the programmer and the memory, no, the intermediary between the programmer and the user of the variable and the owner. But everything goes to the owners, and the owner is like the accessor of the memory. So like, just imagine it could be like the owner is the driver of that. It's accessing the hardware, and all the operation from the operating system goes through the driver. So the operating system or your applications, I don't know, music player or stuff like that, they don't access the sound card. They just send their intentions to events that they want to do, and the driver handles those, and only the driver knows how to communicate with the actual hardware. And that's the owner. You can see that as an owner. So yeah, the difference between shallow copy and, so shallow copy, it will be, so a deep copy is it will recursively go through all the so if you have like a chain, or how it's called, the nested structure. So if you have a struct that inside have a field that points to struct 2, that inside points to struct 3, and so on, the shallow copy could be that it will just copy the, let's say, the first structure fields, and then the actual value of the field that was pointing to S2 is retained, is copied as a value, I mean the pointer, but it will still address the same S2 as before. So that's a shallow copy, and a deep copy is like recursively, it goes all the way down in all these three, because actually this is like it's like a graph because it can come back, but just imagine it's like a tree structure on the folder structure on the file system, and it will go all the way down to the last level, and it will copy and clone everything. Okay, here is that it will uh, it will allocate two regions in memory for the first, for the hello, for the hoy, and will be a new string behind the scenes in the memory that will be used. So here you see that this so string doesn't have normally doesn't have clone, but uh, I think as I know, string doesn't have clone in Rust, but if you would have, you could call clone like that explicitly. And yeah, this is a copy. So here it okay, see, take ownership. Also this here, yeah, it's happening a move, so the actual value is moved, and then x5. This makes a copy because so this is a move like we discussed before because this doesn't implement copy, and this the primitive implements copy. So here it will actually make a copy of the value and it will be transferred by value. And here you can use x because this one still points to the same memory address. This is a new address, so that's why. But you cannot use s, for example, here. Okay. So if you have any other questions related to ownership. Okay, so no questions. Just wait a little bit more. Okay. Yeah. Someone unmuted himself or themselves.
Yeah, I just wanted to say that, theoretically it looks fine. Uh, so right now, no questions are coming up.
Okay. Okay. Then we can move to references. Uh, so all this ownership is okay, is nice, but let's say you still want to have the ability to still use this variable somewhere else in a different context, but not becoming the owner, because what's happening, for example, in this code is if I will still want to use the a here, what I could do is I could return a from this function. So I could pass the ownership back. So this is like a ping pong. So here the ownership is passed to the test function, and then from the test function is passed back to the one who's calling the function. So this again comes back to a. So then now I can print a. So it will work. But then you have this. You need to return this back, and then if you also want to return a value, then you need to return like a tuple or something, or I don't know. This will be your result. So it becomes messy. So this is not okay. And how they resolve it is they have this concept of borrowing. So you could borrow the ownership. Let's call it. You could borrow the ownership to the other context, and this is like what is called a reference. So this is like a pointer in C, and this is, for example, the syntax. So you just put adversant before this. It will just create a copy of the pointer, let's say, and so this is here. So in the S, they have initially the structure with the pointer, and here it copies the pointer value. So this will have the same value. So it will point to the same memory where in the heap where the actual string is allocated. So this actually will give you the ability to still use S without taking the ownership, and then here the ownership is preserved for this S1, and then you can still use S1.
So here with this ampersand, basically you create a pointer to the S1 value that
Yes,
contains a pointer to the heap array.
yes. So the actual pointer in the S1, in the S1 gets copied by value. So the values are copied in another region of memory, and this pointer value, which is the address of
Mhm.
this index 0, is the same. So these two values are the same,
Oh,
and
I think
actually,
that pointer on the left from S, that pointer
yeah,
in S is a pointer to actually where S1 is in memory. No?
correct. Where S1 is in the stack. Yeah, correct.
The stack,
So
yes.
yeah, correct. So yeah, you're right. Yeah. So the value of this pointer is the memory address of the S1. Yeah, you're correct. Yeah. So this is like a pointer in C. Actually, it's exactly like a pointer in C.
Actually, in C++, there is a concept called reference, and references are also immutable. So it's very similar with this.
And they don't have mutable references.
I don't remember. I didn't program in C++ for many
No,
years.
I think they are mutable by default, like in C++. Like I remember that if you had a reference, you could mutate it. I
Yeah,
don't even
there are
think.
pointers and references in C++. So I think the
Yeah,
pointers are mutable, but the references are immutable.
Maybe it could be.
reasoning, thinking.
Oh
what
yeah.
what are you thinking about? Do you know that joke with what are you thinking about? If not, you should look. It is nice. Cannot be changed to refer. Right. So are immutable in the sense that they cannot be changed to point to another one. However,
Yes. But you can
but
change the
you can
value
share.
if you
Yeah,
have.
yeah. So
Yeah.
you have mutable access to the memory, but you cannot change the value that you are pointing to as a reference.
Yeah.
Yeah, maybe it makes sense
And
because
in Rust, can you change through the reference? Can you change something in the string through this borrowed thing?
no. So I mean, it depends. So let me write the code just to make it clear. So they have, like, for example, here we would transform our structure to be, let's make a string like them, and you make it like this. So this is a reference. So this is now uh, a reference that is immutable. So if this string is it cannot be changed in the function. So it's immutable, and because there is an interesting differentiation here. So this is immutable. If you want to change it, so if you want to change the value in string, you make the reference mutable in the idea that to what the reference points to, it is mutable. So this allows you to change the string, but you cannot do, for example, here you cannot do a equals another string like this, for example. So this is exactly, so this situation, this representation like this is like you had in C++, we looked before, that the reference gives you ability to change the memory that is pointing to, but you cannot change A to point to something else. So this is not valid. In Rust, what you can do, maybe there is also in the C++ ability, you can make the variable mutable. So you could make this mutable, so then A could point to something else like this. So then you can mutate. I mean, you can change A. You can change A, make it point to something else. Let's say like this. So this is different. That's why this mute. It's important that you understand it's different because this is is giving the ability to mutate what is pointing to, so the interior memory, and this gives you the ability to mutate the value of the pointer. So this is like a pointer, and it gives you the ability to mutate the value of this pointer. So like this. So like I will change the value of this pointer. So what I have here, I can make it to S1, S2, and stuff like that. So actually, this is what a normal one, which is not. So this, like this, is just like you have here, and once you set the value here, that's it. You cannot change it. And if you want to change it, you need to make this mute. So then this S, let's say, will be the same. It's S. Then it's being able to change its value that it points to. So you can point to something else. Okay, and I think here are what they are. Yeah, they are speaking here about that. This is that. Okay, this is the other concept. So, given the fact that you want to have this ability that only one owner could, let's say, alter the data or let's say destroy it. Let's say so. This the first help that this I explained this manipulability, but so the idea is that in Rust you can have multiple immutable references, so you can have as many as let A2, let's say 3, like this, let's say. So you can have many immutable references, but like you see here, you cannot have two mutable to the same one. So you can have many immutable, or, but this is an exclusive or, so one way or not the other, or you can have only one mutable reference. Why only one? Because one thing that is protects you it is if in C you can have let's say double freeze, I think it's called. So you can have a variable, you can call drop on a variable on a pointer 2 times, and it will call the destructor 2 times. So you could actually do something that it will clear the memory first, and then if the thread stops and another execution actually use this memory which was free, then I think you can add something else and you can clear it again, which is not correct. Or you could have, like in the drop, you could have some logic that is not what is considered idempotent. Idempotent is that you can execute it multiple times and the effect is the same. Like for example, a read operation. If you read something from the cache, let's say, it doesn't change, you can read as many times as you want. But if you write, let's say, increment by 1, that is not idempotent because the effect is different. You actually change the value each time. So each time the result will be altering the value. So that's not idempotent. So this will not be valid. So that's why Rust is helping you avoiding that by not allowing you to have multiple mutable references. Also, another advantage that it gives you, so it protects you also from data race condition. Data race condition is that you have two threads, for example, which are writing to the same value, and you can have, like, I don't know, like the singleton pattern, where you compare if the variable is, let's say, not initialized, and you do this from two threads, and let's say the execution after you execute the if, it gives you true, that is not initialized. It moves to the other thread also, that's the result is true because it's not yet initialized, and then both of them will continue and initialize the value. So you will end up initializing the value twice, and you actually call the initialization function, let's say, twice. Of course, let's say in the actual pointer, you will keep only the latest one, but you actually called 2 times. So you could even, if from the initialization method you return the pointer that you actually allocated, then you'll actually end up with two references, 2 pointers in different location in your code, in different contexts, in different threads, which will actually point to the different memory location, which normally should be a single memory location because that's why it's called singleton. So actually you break the invariant. The variant is that the rule that it should not be it should not vary. So it's like a rule that it should not change. So the rule is that you have only one place in memory wait for that stuff. Let's say, or like you can imagine an account. Let's say you have a structure that corresponds to your wallet. I don't know, wallet on the crypto or even the real wallet or something like that. So if you end up with two wallets, then if you take money from one or put money to another, then which one is the real one? And is not correct. So this is so the borrowing is giving you the ability to, let's say, temporarily own that variable and do stuff with it, but it has this limitation that you cannot have two mutable references, so that you don't end up with a situation that we discussed before. And also, what what is protecting you against is the same. If you could have like so the idea is that let me see the example. Maybe you can explain one example. Yeah. So for example, here, what's happening? So normally, this given the string is allocated here. So this is not valid code because of the fact that if you allocate the string here, this is the owner. When the function goes out of scope, I mean this variable goes out of scope, the function finishes. This gets destroyed. So the value, the memory allocated for the string is gets destroyed. But if you would be able to return a reference to it after this, you would have the ability to actually read from that memory which actually was destroyed. In C, for example, you can do this. You can send a pointer to something, and then along the way, you can call the destructure for this object, and that pointer, it doesn't know that you call the destructure, and then it will use the memory, and it's invalid. So this actually uh, helps you not to get to that situation. So this is how Rust helps you not to get to that situation, and this is the idea that as a rule you cannot return references to local variables or something like that. It should say. Okay, with life cycle is a bit more complicated. Yeah, this is the error. Cannot return reference to local variable. Yeah, this is the idea. So this is not possible, and it's good that is not possible. And instance of string. Okay. This is the same. Just that they explain it. Okay. So this is the same. Okay. This okay. 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 The difference here is that here it doesn't return a reference. Here it returns the value. So this is a move. This is what's happening is a move that the ownership of the S is becoming the caller of this function, the one who is calling this function. When? So that, yeah, that's what's happening. Okay. So if you have questions related to this. So this is all clear. No questions. Okay.
I actually have one understanding actually, Gab, that in the examples in the Rust book and even in while we're programming as well, in some cases we are using the string, when the data type string, when we are passing or using that variable string type variable any, or I mean my question is not exactly aligned with the references and borrowing, it's just a kind of use case kind of question. And in some cases when we are using ampersand str, to reference that string variable in some cases. So my question is that, is there any specific rule that when we should use that string type and when we should use the reference? I mean, is there any thumb of rule, or maybe something, some standard practice, that when we should, defer this thing, or how we should approach it? I hope my question is clear.
Yeah, it's clear. So the idea is that if you use this like adversans stir. So actually, what this actually means. So this is where lifetimes come into play. So lifetimes are a way to. So the compiler is very smart, and it tries as much as possible to do a good job, and it does in identifying situations where you would end up in like a dangling pointer that we seen before. So it will not allow you to do stuff like this. So the situation that you return a pointer, but the memory of the address it will be deallocated, or making sure that it doesn't deallocate the memory while, I mean, not allowing you to have a place where you could deallocate memory while there are still active pointers. And this is, you wanted to ask something. Okay, so this is what the compiler tries to help you with, but there are cases where he fails. So in those cases, sometimes you need to help him, uh, give him some hints, and there is where lifetimes come into place. We'll discuss a bit lifetimes a bit, but this is like how you define the lifetime, and this static. So there are some specific type of lifetimes. The static ones means that this. Variable is actually statically allocated. What this means is actually like you would have in other, also in C, I think. It's very similar concept. You can imagine, let's say, you would have like, let's say, in other languages, something like this, uh, which what it does is actually while your code is being compiled, these static strings, or also strings that you are used all over the place, are actually collected and put in a region of memory where your program resides in a fixed place, and they will be used from there. So then these are actually allocated, and it will exist for the whole duration of the program. And also this if you do like stir like this, it will actually behind the scenes it will make this lifetime static. So this string will be available for the whole duration of your program.
Okay,
So
so if I understand correctly, when we are using the reference type, the ampersand str, we have to go with a lifetime annotation. We have
yeah,
to provide that.
no. So for the string, for the stir, this is so these two are equivalent. So the compiler behind the scenes, let's say, does this for you. So it will make this reference static, because behind the scenes it will anyway make this allocation static. So
Okay,
this will be static. So you don't need, this is like a sugaring, or so code sugaring, or how it's called. The idea that is easier to write this, but is equivalent to this. So this is a static.
okay,
So
so
the idea is that,
similar.
but as you see here, the reference is not immutable. So this is a reference to a variable. So this variable becomes static. So this is somewhere static in the program. And for example, if you have, for optimization reasons, it could even do, if you have, for example, like this, it could even do like in the memory, it will actually store AAA only one time. Like this will correspond to what's in the memory. And the actual A and B will be references to the same memory. So for optimization, it doesn't make sense to allocate these two times, because you know that this doesn't change, cannot be changed. So then it makes
Okay,
sense to make references to it. and just use the same value, because that's like a constant that will be not get it will not get changed. And this is, for example, if you want to use in your function, you just have something like print something, you want to print a string, and okay, you print it. Then in here you don't mutate it, so you can just pass a stir. It's perfectly fine, and then but if you want to mutate it, so for example, if you want to, but even if you want, for example, if you want to print, it has like this. So if you want to print the the b, you can mutate it, for example. Okay, you need to put mut here also, but
Okay.
the idea is that you can mutate b, so you can change b. So this will be, let's say, the first rule, or I mean the rule how you can decide if in your function you need to use stir or string. Because if you want to mutate it, you need to, let's say, you want to use reference to it, or you want to change the value, then you need to use a string. Only string gives you the ability to actually change the value inside. This is how you decide which one you want. And for example, here, if you want to call b, if you want to call a print with also for the b, for example, you could use as stir, or as I know, they have their print. It's my print. Okay, print. Okay, the idea is that you can call a stir, which will give you a reference like that, or I think you can also do for strings. You can also do like this. So uh, let me think. I think you can also do this. So this will be explained later on. So there are some interfaces that are some traits that are doing some, let's say, automatic for you, like copy does. You've seen that behind the scenes, it calls clone for you, the compiler. This also does
Yes.
some magic that uh, it will let's say, there is a trait called as ref, and if you implement that, you can decide what it will be given for reference to. If you want a reference to b, it will give this. And I think the compiler for the string is implemented automatically, or in the standard library, and it will automatically create an as stir for you. So it will automatically create a stir like this for your string. So you can call like this too. But to answer your question, long story short, is that if you need to mutate it, you make it a string. You decide if you want a reference or if you want to move it. But if you just need to just print it, you can just do stir.
Okay. Okay. So in case I have to modify the string or further process it, then I should use that string and use the mute keyword in
Yeah,
order to make it modify it.
yeah,
And if I have any kind of static operation, let's say to display it or to concatenate it with something else or maybe something static, I'm not sure about
yeah,
the concatenation,
yeah,
then I should go with add ampersand str.
yeah. If you just read the value, yeah, you do whatever. But if you just read it, you can just stir.
So with stir, I cannot do a replace in the string.
No, I don't think it's logic. Let us check, but I may be wrong. But as I know, it doesn't lie. I don't even know. It doesn't have autocomplete. I have an example.
Maybe you can open Rust rover or something.
Can open us root.
So by default, when you do let s equal string literal, it creates a star.
Yes. Maybe let me see. It doesn't show. It should show. You just index. You see? Yeah. The raster puts the type. You see, it is star. So automatically, the type is like
It
that.
will help if you can zoom in a little bit.
Yeah, sure. Wait. You see? So it is a star, and it doesn't even have. mm, It has only this index on insert. This is from ser the JSON. This is some blanket implementation. So this is implemented automatically by others. So actually, you cannot do. I think it has cars. Doesn't even have cars.
So I cannot say s of 0 equals b.
Yeah, you. I don't think you can.
Maybe you have to make it
Not
mutable. Maybe you cannot even.
cannot index by integer. Okay, so it cannot even index by that.
But I suppose you can print the first character from the string, right?
I don't know exactly. Maybe the editor got something, but cars. Okay, so then why don't I have cars?
I think that normally, oh yeah, you have the nth thing, and you can turn it either into chars or bytes. But I think bytes is only for string, not.
Yeah, but I
Directives.
don't have cars.
Oh, I don't know that. I can try it. It works.
Like compiling, but it doesn't show in the auto completion. Oh, why is it taking so long?
Well, it looks like a very heavy weight. Is this JetBrains or what?
Yeah, it's JetBrains related. Yeah.
Ah,
It's called
it's
Rust
heavy.
Rover, but okay. So what it did? It didn't print anything. It didn't put print. So it has. It means it has just print line. What? I think my editor. Okay. Don't need to understand this. Okay. Okay, so my editor
It's
is
an option.
yeah no but yeah but I mean my editor is gone crazy but because it doesn't find cars but obviously it compiled and it even ran so my editor is a bit crazy.
Oh, you're using Warp, the one that has the AI integrated.
Yeah,
Token.
just I don't quite use the AI. I'm not so fan of AI.
You have to buy tokens anyway. So yeah.
Some stuff with AI with it works but I happen to have it considered practical one time. I was connected SSH to a remote server and I didn't have some packages installed and it actually suggested how to install them and it was not for example, for one package, it was not like you just install it with the package manager. You need to and install it, and it suggested actually that. So because it's okay, learn on the internet from their documentation, it's actually suggested the curl and so on, and run into the SH,
Yeah,
and
yeah,
so it was practical for that manner. That it was actually good for me.
yeah. Yeah.
Maybe I didn't comment it something very well here, but the problem run. Okay, so that one is crazy. Okay, so I think yeah, you see, so what replace does is actually returning you a string. So it's creating a string from this, and it's actually returning you by move. It's returning you a new string, which you can then also continue to mutate. So this is not mutating the actual s, because if I do replace from 0 to 1 and give it, I don't know, something, I think, no? Star. Uh, ah, okay. Replace. So if I print like this, it will be the same value. So the actual variable will not, be overpowered again. I don't understand. Sometimes I really don't understand. So Rust is very good at runtime, but is the worst at compile time. So in this case, I don't know why it needs to compile all the crates, because I just changed in this file. You should only compile this crate, this file, and it's okay. It's VS Code, but it stores in the same place. The value from a string. Okay, from A. Okay, from A to, why doesn't like star. This should work. Crazy. So you see, the our the actual s is the same. So it's not replacing the actual content of the s. It's actually returning us a new string, and we need to print b. And if you print b, it will be empty in this case.
You are still printing S, not B.
Too bad. Oh, see, it was fast. I mean, I was fast. I changed before the compiler managed to compile the code. So you see, this is clearly that S is not changed. Okay. Okay. So, any other question related to this, or we should? I think we should move to questions, because I think we overextended already too much. I mean, questions. If you have other questions related to 4, 5, and 6, because we didn't even cover 4 at all. I mean, all. So if you
Yeah.
have, yeah.
Well, if nobody wants to, I'd like to do like a live review if there's time for that. If not,
Yeah, so you would want to present your code?
yeah, why not? I mean,
Yeah, yeah. So let us see first if others have any questions for
yeah, yeah,
all for all three chapters. So four, sorry, 5, 4, 5, and 6, which you should study until next call. So if you have any questions now, please do from all these three chapters. I don't know how far you are along.
Sorry, but the explanation and overall it got a little bit overwhelming for me. I couldn't grasp the entire thing. So if you can, summarize the thing a little bit, that how both things are different, or what will be the exact use case for str and string. I mean the example and all those stuff. I just went into the rabbit hole. It. I mean. Still couldn't
But
figure it out fully.
for what more exactly? Borrowing and I mean ownership and borrowing, or string and stir, or what's exactly the
String and
question?
str are basically, any prominent use case, or where it went different, or what is the difference, if in a in simple manner, if it can be explained. I just
May-
lost while the explanation.
Maybe can I try to also make a short explanation of what
Yeah, yeah,
the
sure.
uh,
Please do,
stir is to make sure that I understand it correctly.
please do.
So stir is just like it's storing just a start index and an end index in one of in a in an actual string object.
So it's actually just holding a reference to. So the string, the value, it's saved in memory at a specific location where all strings and constant statics goes, and then the stir to that is actually pointer to that starting character, the first element in that array. So it's like we see in the string. Where they speak about it, and the ownership, I think. So it's like keeping this hello is the string value. This is kept in that static region of memory, and then the stir is actually this pointer. So it's a pointer to the first index, to the first element in that the first character. So then it knows, and okay, you can see it like also because it knows the length. It knows the length. The capacity doesn't care. So it knows the length. It
Yes,
knows
yes.
how much. Yeah, it knows how much to copy from that. Like for example, in C,
Okay.
they write the terminator /0 at the end of a string, so then you know where to terminate. But here they keep the length, so you know how much you can read from it.
Okay, okay.
Sorry, but for me it's not clear why we still need the star besides the string.
So the star is like a constant. So if you just need constants in your code, I don't know if you have like field names that they don't change, so stuff like that. If you just need constants, static constants, you can do stir. Or if you have context where you are enough, let's say with a pointer to something, so somehow the stir is like the sugaring, or I don't know, something easier for you to, like a string that is always immutable. And then the string is then something that you can actually mutate and use like a regular string that's modifiable, that's mutable. So this is allocated on the heap, and then it's actually, so the in the, memory allocation for the program, there is the stack where this all this stack and the primitive, let's say, goes, and then is the heap, which is a bigger region that is also can be increased, and there is this also this static memory where the statics and constants goes. And actually this is a memory separate from the, so similar to, you can see it like uh, the the first one, and then it's just to the stack, but it's just separate, and it doesn't change. So it's just statically allocated because it knows from the beginning what constants and what strings goes there, and it knows what to put there.
So star are always constant.
Yeah, are like constants. Yeah. So you can see them as constants, and also you can see them as pointer to, let's say, something that you don't need to change. So it could be used in, like I gave example there, it could be used in situation where your function accept like something just to print, and you can also use string just to print it. You can transform it into a reference like this. So as star, it will return a reference like this. So behind the scenes, it can return you, because the string has this internally represented, so it can return you a read-only pointer to that region of memory. Excuse me, just a minute. I'll come back. Just a minute. Sorry. I'm back. Sorry for that. So I don't know, just as a rule, you could just see like that. So if you want constants, you use stir. I don't know if you have field names or something like that that you know that will never change. If you need to keep in your structure somewhere something that you want to change, you need to use string. So then you can mutate it. And in your functions, if you the same, if you want to get you want to receive something that you want to mutate is a string. But if you just care about something to just want to print, you can make it as a star. So just imagine somehow this is a this is also similar to I know like polymorphism. So in polymorphism you could have like just imagine you could have like a trait or interface in other languages which is I don't know a list, and then you can implement in various ways that list. So you can have it like a normal vector which allocates a memory with an array inside, or you can allocate like a linked list, or you can I don't know, do all other combination. You can do a list that saves the data, I don't know, in the on the network, so fetches the data from the network or stuff like that. And if you have a method that just wants to, I don't know, iterate through a list and print the elements, it doesn't care the underlying implementation so much. You will do a method which will accept just that trait. So you'll have your list accepting. Let's make it a pointer that you don't want to I'll get it here. I want to move it here. So you have your the list, let's say. So you have the trait list. So you don't care what's behind the scene. So by design, you make your methods as let's say generic as possible or abstract as possible. I mean, you pick the highest interface in this chain, in this tree, that fits your needs. If you don't need anything more, you don't do it anything more. So, for example, if you want to have, let's say, for example, a set, so there could be like sets which are unique elements, list with unique elements. But for example, you could have like an implementation of a set which is also sorted. Let's say it keeps elements sorted. So if you don't care about that, you just use a set. If you really care to be sorted, you will use like sorted set. So then you accept only the sorted sets, which can also go beyond and have all type of ways that you sort a set. For example, B tree, binary tree, doesn't matter. You do all kind of heap. You can have all kind of operations. So somehow you can see the stir in that analogy, like the highest in these three, and let's say the string could be like a star that's also mutable. So it has the ability to also mutate it. So from here, it's also the star could start with this representation with just the pointer, and then your string actually, which actually give you the ability to mutate the star, and it has the ability to have the capacity which initially how much is initialized the length that is now that you can also increase. So string is like the child interface, let's say, or the implementation of the stir. So if you just care about printing the stuff, you can accept a stir. So you should design your interface as generic as possible. So stir is more generic than string, let's say. Is a more generic version of string. Uh, does it does it help clarifying a little bit more? Or if it
Yeah,
doesn't,
better actually, much more.
Okay. Andrei, does it, you are still here? Yeah, you're here. Does it
Yes,
help you? Does it help you or not? Still not clear.
yes, a little bit understanding that star is a little bit more generic than string.
Hmm.
It's still
Yeah.
not clear all the ways in which is more generic, and I imagine that is very similar to a immutable string somehow.
Yes, just the difference is that it doesn't have all these. So, for example, when you allocate a string, even if it's not mutable, it will allocate an array internally of the size of the capacity. You can specify the capacity, how long it should start with. Also with the vector, you can the vec. And the idea is that even if you have only one character that you allocate, if you don't specify by default, it will use something. I don't know, let's say 16 or something, and it will still use that memory, being prepared that you will add to it because that's why I use a string because most likely you want to add to it. So it uses more memory than the actual data that it is there. But if you use a stir, it will exactly use how much is allocated, and even more the the when you allocate a string, it will allocate it at runtime. So at runtime, it will execute the code, it will use CPU, it will allocate memory, and have this done, have it done for you. But if it's a star, then given the fact that the compiler knows that it's constant, like it knows, for example, how to inline some stuff. In this case, it knows that this constant will never change, so it knows that it can include them. So actually, these are included in the binary of your product program. So when you compile your program to
Mhm.
become a binary, this will include it in the binary, and when the program will be loaded into the memory, it will actually be copied from that file into that static region, like perm gem is called in Java, something like permanent general stuff like that, and it will actually copy from your binary file to that region in memory without executing the code to allocate it. So it just copy it, and you can then just use it. You have references to it, and all your
Mhm.
program logic that have references like stir from that, it will actually just be pointed to that. So you skip the allocation. You do the allocation like compile time, let's say. So that's let's say
I
a big
mean, at
difference.
program loading, not necessarily at compile time.
Correctly. Because at compile
Okay.
time, yeah, you're correct. Yeah, because at compile time, you actually execute the code that will create the, let's say, the memory footprint for that string. It will embed it in your file, in the binary file, and at runtime, it will just copy it. So yeah, you could consider that then it actually goes into the memory. But I mean, the logic that it will be executed to allocate the memory footprint, it will be executed at compile time. The logic. But then the actual bytes that were created are just transferred to the file and to the file at runtime to the original memory, which OS does that for you.
Okay. I mean, understanding that that thing that the star allocates exactly a piece actually that they are allocated, they are written in the binary and they are
Mhm.
exactly as long as the literal itself.
Yeah, and
Uh,
one also because it's very important related to this. So given the fact that this stir, these constants, and also the constants. So just be careful also about the constants. Actually, the constants no, because they are embedded, but they are still included in the binary. So also the constants, the static constants, and the also the other constants, but especially the string, because those are where the problems appears, arise, are are included in your binary. It's very important to understand that if you open with a hex editor your binary file, you can actually see those strings uh, readable, human readable, in the content of your binary. So if an attacker analyzes your code, your binary code, and if you have there some credentials like passwords, I don't know, something that it's a private data, so it could compromise your execution or you, they have access to it. So you need to pay attention not to put that in there. So if you have like credentials that you want to load in and use in memory, never use a stir. Always always use like I mean, don't keep them as a stir. I mean, in the in the memory so that they will copy it in the binary. You could have function accepting there's a stir from a string because the string is allocated at runtime, so the attacker cannot know the value if he's just looking at the binary. And well, when you are creating them and putting them at the runtime, okay, depends where you are copying them from. Maybe you are copying them from the UI, from an input field, or via the standard input or something like that. You copy in the memory. And also, what's very important, just as a rule with credentials, is always after you finish using them, most of the time is in the drop of that structure, always zeroize the memory. I mean, write zeros on this array, because if not, what's happening is when your memory is deallocated because of optimization reasons, the compiler doesn't, I mean, the executor where your program run doesn't clears this memory, so this data remains in memory there. And because it's for optimization reasons, most likely what it will happen, it will give it to another program, or even the other thread, or even that program of yourself. So it will give it to a different context, which will actually go and write their data there. But let's say if the other is not writing their data but directly reading, they will read your string. So if that's a password, they will read your password. So that's why it's very important, if you keep encryption keys, password, anything that can be compromised, that can compromise something about your program, or you, or anything, you need to zeroize it. So after you write, you keep finish it, you need to zeroize it. It's very important to do that. And you cannot do this if it's a stir, because if it's a stir, it's all you see that even if we call it replace, it didn't do anything on the stir. It creates another one, and even if it will allow you to do this in memory, even if it somehow allow you to write that static memory, let's say with some hacks, in the binary of your program, they are already embedded these credentials. So if the attacker has access to the binary of your program, it's a problem. So if they have access to the memory of your product, then most likely they could have access to your binary, because having access to the memory is harder than having access to the file. So that's very important. Don't keep important stuff in as a stir. Just keep constant that you don't care if somebody else would see, like field names or stuff like that. Also, if you have field names that have something that can compromise something that is compromisable, the same. Apply the same rule. Okay. So, if you have other questions, please. If not, then we can move to Anthony and have a peer code review. Peer code review.
Yeah, I'm very curious.
Yeah.
Do I share my screen?
Let me stop. Maybe. Yeah, stopped now. Maybe you can try now. Just I need to locate your. Yeah, I can see. I can see you.
You can see it.
Yes.
All right.
Yes, we can see.
Which one though? Wait. There's this one. I think this is the first one, and this is the second one.
I think we should. Yeah, we should do the first one. The second one is a bit more. It's a bit more advanced.
Okay. Do I read this as well?
Well,
Or like a small introduction?
yeah. Go ahead. Yeah. Do a small intro.
So we have n numbers that are generated, or no, so sorry. We first read the n, which is just a number. We read it from the terminal, and then we generate n numbers randomly from 0 to 1 as floats, in this case as f32, and whatever. And we have to. I don't remember this one because I did the second one recently.
Yeah. I can quickly tell. So
Oh, and we keep generating random numbers in a loop, and we want to see how much it takes until we hit. That's how I called it in my
Yeah,
code,
it's good. Yeah, it's good
all
technology.
the n numbers basically. So we're
Yeah,
playing
so
with a random number generator on the.
yeah, so somehow it was an extension of the guessing game. I mean, you were exposed to the random number generators in the guessing game in the book, and I was thinking what problem could be interesting and somehow also have a association in your use case or something like that in your world. And what the idea came from the fact that in the Bitcoin, because everybody knows about Bitcoin, so they have this idea that what's called mining. So what mining is they have this terminology called proof of work, which actually you need to do work in order to gain tokens, let's say money. So the idea, what they do is it's similar, just they use hashes and so on, but we don't want to yet just yet go into those. But it's similar. But the concept is like just imagine you will have like a lot of boxes where somewhere in the world, and some of them contains money, and you don't know which one. Okay, so you don't even know the distribution. It's not evenly distributed. It could be anything. I don't know. It doesn't matter. So the idea is that you then will go and open each box and then see in which one is money. Okay, and then you took money. And the idea is that it could take you a lot of time, So depending on how many boxes are there, and how few of the tokens are, it could take you a lot of time. So that's the idea. That's the work that you do in mining. For that, you actually need a lot of compute, and you actually need to generate like these values which corresponds to the let's say the number that is written on each box, and you actually by generating each of these numbers randomly, you actually go, this is the analogy that you go and open the box. So that's the work you do. So yeah, as you saw, it takes quite of time to generate all these possible number that in the end you end up with that specific value. That's the box index, and okay, those are the money. So you take money. Yeah. So
Yeah.
no, please go ahead. And yeah, so somehow if you mentioned you did the second one, so just an intro to the second one. If you have time, we go to the other one. So the second one, the idea with the second one is, let's say we have some additional information. So we also know. So if you generally randomly generate these numbers in that array of I know something, the idea is that the there could be some intervals in 0 1, or okay, here I put just for simplicity 0 1 billion. Okay, so just imagine you have these 1 billion boxes, and so some of them are the lucky ones. So there could be intervals which contains more lucky boxes, and if you have this information as a hint that okay, look, in this interval 0 100, or okay 1 100 stuff like that, are that will be zero. I missed Rod.
Yeah,
So
yeah,
yeah, okay. So the idea is that if in that interval are more, it will make sense me as a looker to go in that interval and open more boxes in that interval, not go into the interval where there are less or maybe none, because with this. So this is the weight. So the weight is telling you how many lucky boxes are in each interval. Okay, the ones with zero, it's zero. So that then when you pick, because that's the idea. Okay, you could take the weights, order them if you really want to maximize your success. You take the weights, order them, and you go to the interval that has more boxes logically. But the idea was to also learn about weighted random distribution. So what this weighted random distribution is, because if we speak about random, is that normally the random gives you numbers uniformly distributed in that 0 1 interval. So if you generate just I don't know 10 numbers, maybe they are in a part of the interval. But if you keep generating, you will see a trend that all the interval. Let's say if you put points and draw them on this line, all the points will have a similar distance between them. So this is a uniform distribution. It will distribute uniformly on all these intervals. So you maybe want situation where you would like to distribute more of the points in the, I don't know, first part of the interval or somewhere. So then I gave an example on the chat that maybe you want to create a simulator where you uh, generate like soccer or football sport games, and then you have like for example, it's not very common that somebody, I don't know, makes I don't know, gives 10 goals, I don't know the term, hits 10 goals or something like that. Is because okay, it's very hard. It's more popular, I don't know, to hit somewhere between 0 and 3, and maybe the most popular is, I don't know, 1 or 2 or stuff like that. So if you want to generate realistically, you could take which scores are more probable to happen, and you can take this from a history, for example, if you want to be accurate at least with the historical what it will happen, so to the real data, and you can actually set that weights as the okay, you could take all how many times each goal have happened, you sum them, that's the sum, and then you take each one and put as weight. So then you have some numbers that it's telling you how much likely it's that to happen other compared to others. So that's the weight distribution. So there are algorithms you can use libraries at first, but there are also algorithms that, I mean, how the library is implemented on how to generate these random numbers, taking into account that probability distribution.
Yeah, I even have an example here. Yeah, I
Mhm.
generated 10 numbers. You can see the numbers here. And then the program generated a list of intervals. And you can see that in the interval from 0 to 99, we have only one number. And for instance, in the interval from 700 to 799, we have three numbers here. You can actually see them here,
Yeah.
19, and yeah.
Very nice.
I didn't generate them to 1 billion, but it's a
Yeah,
constant in the
it's
program,
okay.
so I
Yeah.
can change it. And you can even see that we got lucky, and it decided to search it not decided, randomly generated to
Yeah,
search
yeah, but
in the
uh,
seventh interval, and it
but this
actually got a hit on the
actually
first try.
that's the idea that if you run this program multiple times, most likely, I mean, in the many cases, in much of the cases, you would end up generating in that interval, because actually that's the point.
Yeah,
Randomly, it will most likely get you to that interval, and yeah, you are very lucky that it was for the first time, indeed.
yeah, and you can see here that it wasn't really for the first time, the second time, so it took some time to
Okay.
hit the second one, but yeah.
Hmm.
Now, for the first problem, this is like a C habit of mine. I declare all my stuff here to keep track of them. Maybe I have some other stuff here declared, but most of the stuff is here.
Hmm.
N is the number that we're reading. Randoms is the numbers that we're generating randomly, obviously. And hits is a vector of bools, which basically says which like which randoms we manage to hit when we
Hmm.
search for them, like randomly generated and blah blah.
Yeah,
Count, I don't really remember what count was. Oh, it was the length of randoms that we uh,
that remain, I think. Or no?
no.
Yeah, there
Actually, it was
are.
0, and it was how many hits we had. And when it reached the randoms, I would
Okay,
break
yeah.
out of the loop,
When it's
basically. Yeah.
length, yeah, I understand. Yeah. So how many
Yeah.
hits? Yeah.
And
Yeah.
tries is just for benchmarking to see how many tries we had
Mhm.
before we managed to hit them all. So before count was the length of randoms, and guess was just an auxiliary variable where I would just get my random number. I'm not sure if making it -1 here is relevant or not, but Rust, I think, tells me to initialize my variable, so I just did that. Here I just read the input normally like in the Rust book. This is the same thing. I used unwrap because I didn't want to go with
Yeah, it's
matching,
okay.
and
Yeah, sure,
it's
sure.
just
No.
a small
Yeah,
program.
and that's for
Uh,
later anyway. That's not the point for this. Yeah.
yeah, and here I generated the numbers. And I used push. So in like I just pushed whatever this thing returned, and I generated them from 0 to 1. And obviously, I also pushed at the same time on hits false. So basically, saying that whatever I have in randoms now is hasn't been hit yet. Basically,
Just a question here.
yes.
So would it be possible to move the declaration of these randoms, to move it after
Outside,
you read no after you read the number n and allocate it from the start to be as long as n,
yeah, of course. I actually did
to
that.
have an basically to have an
Yeah.
numbers, the vector to be exactly n
Yeah, I
from the
did that
beginning.
on in the second program. I did that because I first read n, and as you can see, I generated the vector with
Uh-huh.
capacity of n.
Yeah,
So
and
you can do that.
by the way, this with capacity, for example, is the analogous of what you seen in the string, the capacity field. So that's how long the initial, let's say, array behind the scenes that string is using is getting allocated, and this is the same with the vector. So the vector allocates this capacity. So then after that, it will grow and do the copies and so on. It's the same thing. And yeah, it's more it's like a subtlety, but like Bozo, like Andrei is coming from C, where everything is efficient, and also in Rust it should be because it wants to replace, or okay, being a safer C, not necessarily replace it like that. You also need to be efficient, but the idea is that in these cases where, for example, you know that you will not grow bigger, so you know that the size is fixed, it makes sense to
Yeah,
specify from the start. Yeah.
and we could also use the macro, the vec macro
Hmm.
or whatever.
Yeah.
Um, yeah, here I just print the randoms, but that's not necessary. And I've seen, I've asked ChatGPT how to get the time, and it mentioned
Yeah.
something about
It's okay. It's
instant.
okay.
Now
Yeah.
this is
Sure.
not. This is for benchmarking mostly.
Yeah. Sure. Sure.
As the loop,
Sorry,
yeah,
I have another question. Are those specifying the types? Is it necessary or I, if I
it's a
remember
Visual
the
Studio
It's just
doing this.
visually. Yeah. Visually.
Yeah.
This he didn't wrote that. You see, it has
Yeah.
oh
highlighted in gray. Yeah. Yeah.
oh
This is how it looks if I do it, and otherwise, it's just
uh
Rust analyzer doing this.
this is what
What editor?
Visual Studio Code.
this is Visual Studio Code. So Visual Studio Code has this plugin that
Yeah, I think
shows you
all
the types automatically.
I
Okay.
think all modern editors like have
Yeah,
it. I think
you can disable it.
Vim, Z,
Yeah,
Helix, or
yeah.
how it's called, all have this. Neo Vim, sorry, Neo Vim.
Yeah. I don't really like that. I would like to have the maybe the types to the right at the end of the line, but
It does
But the
that
idea,
in
the,
line
for
it's a little
functions.
bit.
the idea is what they are trying to do is mimic what it will look like if you write them. So because this will be the syntax if you rewrite them. That's why they are doing this.
Yes,
So
yes, I understand.
they try to make it. I don't know. I
Oh,
forgot the
I
term.
use, I don't know, some other languages with some different plugins, and they don't put it there in line. They just
Understandable.
show it as a comment or something at the end of the line that it's clear
Yeah.
that it's coming from the.
Yeah, it's okay. It's reasonable. But just imagine, for example, you can have like tuples, where you can have like I don't know what tuple like with I don't know five fields or something, five items. So then if you need to look which one is what in the right, you don't see exactly. But here is actually like you define them where you write them. So in the context you see there in place in line. So it's more practical.
Okay.
Or
Yeah, but you can
like you have
disable.
the function names, for example. I mean, if you would, okay, you're not allowed in the function, you need to put it, but if you would be allowed to use this type erasure also in the functions, like in Python, for example, and if they put them somewhere in the right where you don't make a direct visual connection, it will be harder to identify them. That's why it's like this somehow it's easier. But
Okay.
yeah, like
Sorry
like
for
like
the not for the
no
question that is
no
not
no but no
related to
no
the code
no,
itself.
but it is a relevant question because you are an example that you are using it differently. So maybe you get used to having, like you said, with your plugin in the other way, and maybe it's practical to compare how these two plugins, because this is also the result of the plugin, how these two plugins decided to generate, and see maybe which one has more advantage, because like you said, the other one could have the advantage that it doesn't clutter your code. So your code is, let's say, cleaner for the part that maybe you don't, when you don't care about the type, so you don't actually see there like being imposed to you to, okay, look, it, see it. But if you really care, okay, you move to the right, and then you can see the details. So there could be trade-offs in both cases, and the approach that your plugin that you are using is taking could be helpful, for example, in this manner, when you actually don't want to see them there, but you care to see them, so you have somewhere to see them.
Uh, Now I have, sorry for diverging from the business logic of the program, but I see that on the left you have some sort of window with the
Yeah, it's
Rust book.
yeah, you can open browser like web
Oh, it's
pages
a
in Visual
oh, you
Studio Code.
divided the editor in two and you have a
Mhm.
web.
Yeah, that's how I learned basically. So it's pretty cool. It's an extension though.
Uh,
Like I think it's I don't know, web browser or
Though,
something.
how you make it like this full screen? Okay, I use a little bit. I mean, I'm using sometimes VS Code, not so much as Rust code, but I see that you were having it like full screen, so that's like a
Oh yeah,
different
so
plugin.
when you press F1, you go into Zen mode. But you can also
Zen.
press
Okay, understand.
F11.
Okay,
Yeah,
understand
basically.
Zen. Okay, so they have it in Japanese. Okay.
And this is just the browser extension. Like I can open up browsers. I type the URL here, and
Mm-hmm.
then
Yeah,
I can have it like that.
yeah.
It's not very interactive. It's mostly if you want to read something.
It's also, for example, Andre, it's also useful, for example, if you have ma- markdown files in your project, it will render your markdown files,
Yeah,
like you will see them on GitHub.
yeah,
I sometimes use that when I look into documentation in the project I'm working, and also if I change documentation so that I can preview what I'm changing.
yeah.
Okay, so just maybe I don't know, maybe it's practical if we do the code review, let's say, also along the way, I think, or you prefer to do it at
Hmm?
the end.
Sure. No.
So,
Along the
for
way.
example, one suggestion that I would have done, I would have been doing differently. For example, the hits is okay to mark which one are hit, but for example, you could do it without allocating additional memory. So, given the fact that your randoms are in the 0 1 interval, you could use
Mm-hmm.
like a marker value, like for example 42. You
Mm-hmm.
can pick
Yeah.
you
Okay.
can pick your lucky number. Yeah, I understand. You can pick your lucky number. So the ones that are being hit, you mark them with 42. So then actually you know that all others that are different than 42 are the ones that are still being targeted. Let's say, so
Yeah, that makes sense.
then actually use the same memory. You don't allocate additional memory. Just let's say optimization logically it's the same, let's say, but and also you win like a few CPU cycles actually, because you don't need to create those hits, you don't need to put in those hits,
Modify them. Or
exactly.
actually, I still have
Exactly.
to modify the randoms, but still, yeah.
Yeah. I know. The modifying is the same, but you don't need to put the first falses that you did. You know,
Yeah.
you don't need to do those steps. Let's say those. So yeah. This is just like optimization because
Yeah, like a memory optimization, yeah.
I came from let's say environments where the environments were not so generous, let's say, with us. So I was developing mobile application also on phones, Nokia phones, those with the keyboard and black and white screens. So you have very scarce
Yeah.
resources back then, and there was also very stripped down version of Java, for example. So also you had to be very careful with resources, let's say.
Yeah, every byte counts basically.
Everybody can. So, and also if you go even lower, if you go in embedded, and if you go, I don't know, on the IoT devices, watches or stuff like even smaller,
Of
sensors or
course.
stuff like that, or I don't know if you go on the ABS implementation, there you have to be very careful also with every cycle that you execute, everything that you do. It's very very resource I don't know technology scarce,
uh,
or I don't know
expensive
the
or
yeah. So you don't have this luxury of allocating too much memory. Like for
yeah.
example, nowadays your phone is like better than the free instance that they offer you, the free EC2 instance that they offer you on Amazon, for example, or the machine that you if you use code spaces. I really recommend you. If you don't, it's nice. If you just want to spin up the project and just play with it without fetching it locally, so you could spin up an image on GitHub servers, and they give you like 120 hours of free usage for CPU. If you use multiple CPU, okay, divided. But the idea that okay, it's not. I think they give you 8 or 16 gigabytes. So the that instance is not I know not too much, but you can play a little bit and just play a little bit with the project if you maybe not trust it to start it locally with your username, or you can use locally dev containers. I also recommend you that. Actually, the same. It's done with code spaces, the same technology, and so that instance is so your phone is considerably better than that instance. Just to imagine that. So you have in your phone you have like a small monster,
Yeah,
which
it
we,
makes
Yeah,
which
sense.
yeah.
which we didn't have back then.
Yeah, my
even
new
even
phone is better than my old laptop. It has the same
exactly.
amount of RAM, and I think that the CPU is better on the phone than on the laptop.
Yeah, yeah. Also, my watch is way better than the telephones that I programmed back then.
Yeah,
I think also
which makes sense.
my microwave or fridge is smarter than the phone that I had back then.
Yeah.
So basically, we should not care about performance.
Well,
Yeah,
no,
well that's the
it
problem
adds
because
up.
exactly because that's the problem because this is what's happening with this. So the new developers, or I don't know, the not so cautious and not so responsible developers, they are thinking, oh, the more lure, how it's called, the idea that the next year there will be a phone much better than this. Why waste time optimizing my performance? Better make very very beautiful and respecting your patterns and very clean code. Who cares optimizations? Because anyway, when we release this application, the hardware will be better than we are having now, so it's not a problem. No, and that's the problem that if you look, then the application become uh, more sluggish every update, and you are forced somehow if you want to keep up with having the smooth performance and smooth interaction. You have to buy a phone every 1 or 2 years, which okay they like that, but it's not how the development should be done. So you
Yeah,
should not you should not just
yeah,
think that there will be better resources anyway. There will be money, but this is how, for example, also in the AI industry, this is how these LLMs and all this stuff with. So they got to the point. So for example, Grok now released their I know, some version that is competing with the O3 model, and they use 200,000 G100 NVIDIA GPUs, which I don't know is like 10,000 or something like that. One of those. So they use like millions to train the network and also to run it. So the idea is that what happened in machine learning and neural networks actually is that there is so much complexity, so there is so hard to understand anything there. They didn't find the logic to understand, so they wanted progress, and they observe that if we linearly increase the hardware, we see also linearly increase the performance. So they said instead, stay and waiting for the researchers to understand what's happening there. If they will be able to make algorithm that will not need so much resources. But we don't have that. So while we are doing that, because there will be parallel, but that doesn't have results yet so much as they expect. So they just invest because they have a lot of money, like big players in the AI. They invest in and they buy more hardware. And okay, let's run our inefficient code, which is written in Python, so by default is inefficient, at least 100 times than Rust. Let's see. So they just invest more money and make more hardware. So then we get to the situation that we get, that now AI consumes more energy than Bitcoin and all crypto mining did, which I think is insane. If that energy we could use, I don't know, trying to find a cure for cancer or any other disease that you like, or anything that you like, But so this is what it gets to if you don't spend time optimizing, and if you are permitted not to optimize, and if you are not responsible and conscious enough of a developer to optimize without being asked to. So as a developers, we need to also have some metrics that we do as ethically, I don't know, so some type of constraints, so type of stuff that we, let's say, don't go lower, don't go lower with our standards just because we are allowed. So we shouldn't allow this to happen. Let's say we shouldn't do that. You should optimize, but of course you should know when to stop with optimizations. And uh, like the very first rule and the best rule of optimizing is measure first, then optimize, because you need to know that if it's really a problem how it's running now, and then the measurement helps you to see and use flame graphs. Okay, you will see it later on, or who uses understands. Use tools that will tell you what parts of your program are slowest, and focus your time first to optimize those. Exactly like this weighted random generator. Don't pick intervals which are less to which have less numbers, so you are less. You'll make less money if you don't more money. Pick intervals which have more numbers. So this will be the intervals which let's say we could consider these functions which spends more time in execution. So you can see this weight as the inverse proportional of the execution time. So one the execution time. So then you will spend more time in the ones that have more execution time. Actually, it's direct, not the proportional, because you'll pick the functions that are most likely that if you've optimized them, you win a lot of time. You gain a lot of time back. So, for example, even if you would like to randomly pick what functions you want to work on and optimize, you could use this weighted random distribution to pick that function where the weights are the execution time for the functions. If you want another practical example, maybe. That's all. Sorry. Please continue.
All right. So then I started a loop, I guess. If there aren't any, we can talk about this if you want.
About what?
Like about the rest of the code before, or then I can.
Oh, no,
If
no,
not, I
no.
can
No, no,
explain the loop.
explain it. If I see something, yeah, I'll say what.
So obviously
And that's
we
fine.
increment tries because it's it's obvious that right now we will try at least once to find the hit. We check if the hit, if like every actually tries would make sense to be placed after this, but okay, whatever. It's like a small logic mistake. And here we just check if the number of elements that we manage to hit is equal to the number of elements that we have, and we break obviously out of the loop. This is basically like a while loop. And then here I just get a random number from 0 to 1, and I just check for a hit in this for loop, which I've used this thing because I've learned that it returns a tuple where I have the index, like a key value pair of index and value, which is quite nice because I also need the index. I dereference the value here. I check if it's equal to guess. And in the case that it's equal to guess, then that means we got a hit. We just need to make sure that at that position, we didn't have a hit before, because otherwise we just hit that again, which I did print it. I printed it here just for debugging, but we didn't really need that.
By the way, just a small optimization.
Yes.
Let me think if it makes sense. It's okay. I think in this case maybe not, but you can use, so if, for example, if you want to increment with a boundary max value, you could, let's say, assign the value to the variable, like the variable there is also like the variable +1. You put that in parentheses and then call the max function and put, for example, 1. mean, sorry, and put, for example, 1, and then if you, let's say, overflow the value 1, the result of the expression will be kept 1. So if you are like, I don't know, your maximum is like, let's say, 2, but your value is 0, so you permit that it increase to 1, also to 2.
Okay.
You understand? So after you do like 2 plus 1, it will be 3. It will be being back 1. So the idea is that it's a one-liner. No, you don't have an if or stuff like that. It's like, let's
Yeah,
say,
I did.
functional programming style. Okay, but no, in your case, it's okay because you do several other operations. It's okay.
Yeah, and it's for debugging and stuff.
Yeah. That's
Mostly.
what I say. It's okay. Just I thought that it works directly, but it doesn't. But just in other situation where you want a one-liner to like do an increment until some max value, you could use trick like this.
Yeah,
Because
yeah.
no, I mean the numbers compared to the numbers, for example, in Java, where there are primitives and there are objects for these primitives, associated objects. But if you just use primitives, you don't have methods on them. But here in Rust, actually, there are by default like structs, let's say. So if you have like number 1 or stuff like that, you can actually call methods on it. So if you have like my number plus 1 in parentheses and put dot, you actually can call all the methods for the, let's say, int
Yeah, yeah.
stuff like that, which is
Makes
useful
sense.
in many cases.
Yeah. And basically that's it. Like after that, I just print the elapsed time, and I also print how many tries there were, and we can actually run it if you want to.
Yeah, just one thing.
So we just gotta read n, I think. Oh, and actually I have to call it here because and let's say n was the number of randoms, right? Let's say 10 randoms, and it shouldn't take long for 10 randoms.
Yeah,
Let's see.
should be okay.
Oh, there it is. So 8 seconds and about what's that, like 19 million.
Oh, it generated quite a bit.
Yeah, I mean, it
Okay,
depends.
it's fast, but it's are many, let's say, iterations. So just imagine in the in the Bitcoin world, let's say this will be, let's say, hashes. So it will need to generate hashes like 90 millions. But if you also look at how many hashes a GPU can generate, there are some extraordinary fantastic numbers, like in the order of, I think, billions per second or something like that. So it's incredible, insane. And about this, for example, why they generate so many hashes. So there are many values. So like you did the code now, you actually look for exact match, right? I mean, you only when you are
I think
you have the
since
error or not. I didn't
well,
see it.
since it's a float, there is probably like a small error
Yeah, no,
that
no. Is the precision of float, but I mean, you actually
yeah,
the granularity for you is the precision of float, right? The f.
yeah. That's like
Okay.
the smallest. I don't have like I don't know, a
Yeah.
delta that I'm.
Exactly. So just okay. I've seen in other cases, but okay, maybe you thought already. Just a hint, maybe for the others, or so. The idea is that if you want to accept, let's say, an interval or like
Yeah, I could actually
v,
do that
v,
here.
vicinity, you could have like the delta, so that like the error. In mathematical terms, this is epsilon. If you are familiar with the vicinities in the mathematical terminology, so in that manner, you could actually take these two numbers. I mean, the number you generated, the number you have in the array, and if the difference between them is less than the delta, you consider that it's accepted. It's a hit. So it's in the vicinity. So it was like you have small dots, the draw like with a pencil, and then you have like a big marker, and you put the marker like a big dot, and all the points that are in that region are considered hits. That's the.
And
That's
we
the
can do something like that because you just mentioned that we can
yeah, you need to apps. Yeah, you need to more absolute value. Yeah, correct. Yeah, because
yeah,
you
and
you,
let's say
you
we
care
also
because you
accept
care
that.
you care about the distance. Actually, this is the distance between the 2 points.
Yeah,
Yeah.
and I've set epsilon to 0.2 here.
Mhm.
So this you actually mentioned that we can call the methods on.
Exactly. This yeah,
Yeah.
this is
So
this is
we use it here, so it's okay.
yeah, it's okay. It's good. So you'll see that it will be way. I mean, it should be
Oh.
okay. Yeah, the the print is very extensively using resources.
No, but it should have stopped. I don't know why it didn't stop.
So
Let's see.
if guess epsilon if it's yeah, it should have stopped. Why didn't stop? But before you had that equal, right?
Yeah.
Okay. Guess minus one. Can I go a bit to the val again? Maybe we are missing
Oh
something.
wait, zero
The
point
val.
two is like it's probably gonna guess them really fast, but
Yeah, but then why didn't it stop?
I don't know. I'm
Ah,
I'm just as
maybe
surprised.
maybe it guessed them fast, but printed the okay. Didn't exist.
It keeps guessing them. It's like the hits never really.
Hmm.
Why? That's weird.
Put guess. I mean val zero. Just to so this will be should be val. I mean the epsilon, which is epsilon. Epsilon. Sorry,
This one,
So epsilon. Put epsilon zero.
like
So
zero.
yeah.
It's not
So
gonna guess anything then,
Yes,
right?
it,
Or
it
because you
should
don't.
it should
But
because this will be like the equal. No.
you have there you have less than. You need to put it less than or equal.
okay.
Okay, but it was equal before. Okay.
Yeah, I changed it. Uh, let's see. Yeah, so it's working now.
Okay, but why? Okay, so then
No idea.
okay, but
That's
the condition was good. So if it's smaller, then it's a hit, right? So if it's smaller, if the difference is yeah, the logic is good. If difference is small, it all should be bigger. So, yeah. So why didn't like
okay.
maybe
There it
the
is.
maybe the maybe when it does the diff, the precision is something not enough. So the difference it doesn't get smaller than epsilon.
I don't think so because
Put
it's
a
hitting them.
put
Oh no, it's just
it's a
no, it's
bug.
just faster. But you see, it's not hitting. Like if I let it run for
Is
enough time, it's
now
gonna work.
now it's too fast.
No, it's fine. Like it's doing what it's supposed to. It's just not generating any other number. See, it's just not getting 8 and 9.
But why not? Why?
I don't know, it's a random thing. Like it's because of this.
I know, but why would this distance make a difference this time? I don't understand. Yes.
Maybe because it's generating them like wait, is it like a seed
Put
for this?
put a smaller. No, the seed is the it's taken every time. Put like put more zeros there.
There.
Yeah.
2.
It's okay.
So for 10 numbers. Wow, that was fast. Okay.
Yeah.
But how do you check which one you hit? So when
the,
you
the,
see
the,
that the
di-
difference between the
there.
generated value and
The distance, yeah.
Yeah.
If the distance is less
okay,
than
but
epsilon,
how do you see which one you hit?
index.
Oh,
In,
Distance.
via hits, yeah.
the
Yeah.
Yeah,
index
but
of it. The index of it.
okay, so you
So
No,
he generated
yes, but
first the
because you
yeah.
know what's happening there, because you might have in the same 0.1 interval you have multiple values, and you stop at the first one. So
Indeed, yeah.
so you
oh
so
yeah,
for
that
example you could
it
have a
stops at the
value.
first one. Yeah, that's interesting.
You don't
But
need to
no, no,
break.
no.
No,
Actually,
don't break. Don't break.
no. Actually, I can just put this here, put it up here.
Yeah. Indeed.
And I will not be checking for this, say, and I'll just be checking for that, and I can and that and that. You know?
Yeah.
This should
because
work
because
now
then
or whatever.
anyway, logically, this is what it would have happened. Yeah, yeah. But now
Okay.
you need to decrease. You need to increase the number to decrease the precision. Put it back 0, 0, 0, 1 like you had it, or
Like
zero
what?
one. No. You have like 0, 1, which didn't work for us. No, 0, 1. I think didn't work,
Yeah,
right?
no, 02, but
Ah,
still,
0, 2.
it's gonna
Okay.
detect them like super fast. Yeah, no.
Yeah, but it's working. Yeah, so it's okay.
Yeah. That was a good observation. Now this is the default, and
Yeah,
this takes time. Okay,
exactly.
that's okay.
Yeah,
That's good.
that's yeah. Yeah. So for example,
Yeah, it works.
this is also a good example for you to understand that when you don't need that much precision, don't use it. So the idea is that it will make your calculation way faster if you are, for example, if you want to, I don't know, if you care about the temperature of something, but you don't care at a degree like two, 23 degrees point 21, I don't know, a lot of decimals. For example, the temperature in your room when you set for on the thermostat, it's enough for you if you have with one decimal place. You don't care 2 or 3 because you don't feel the difference. Okay, you feel the difference maybe between the degrees and 0 point degree. Maybe you